Welcome back, everyone, to our continued discussion on an introduction to linear regression. In part 3 of our discussion on algorithm theory, we're going to explore the cost function, which is a crucial part of discovering the beta coefficient values for when we're dealing with more than one feature. So what do we know so far? In general, we know that we can create some sort of linear relationship in order to create an estimation. And we know the simplest one is going to be something like y equals mx plus b. And that's the case of simple linear regression because we only have one feature. We also discovered that the ordinary least squares method, or OLS, actually allows us to solve directly for those beta coefficients. I can solve for the y-intercept, that is b, and the slope, that is m. And recall, in terms of coefficients, we just label those beta naught and beta 1 respectively. However, if I try to add in more features beyond just simple linear regression, we quickly see that OLS is not going to be scalable for multiple features. What I also know is that I can translate real data into matrix notation, and back when I did that translation, we discovered a generalized formula for beta coefficients for multiple features. Let's revisit that formula. Recall the formula looks like this. I know that my prediction, y hat, is equal to the sum of some beta coefficient multiplied by its related feature. So every single feature, that is xi, there could be x1, x2, x3, and so on, so n number of features, I'm going to have some beta coefficient for each feature that then I can simply multiply that coefficient by the feature, and I get back out my estimated value, y hat. And now the question is, we're searching for these beta values. How do we actually find them? So the equation below defines our line. How do I choose these beta coefficients? We've decided already that a best fit line is going to minimize the squared error. So keep in mind with this formula here, I have something that directly relates our prediction y hat to our data of x and the coefficients of beta. Now, since we want to minimize the squared error, let's take a little bit of time to understand how we're actually going to define our cost function or loss function. That is to say, how are we defining our actual error that we're trying to minimize, and how can we relate it back to these beta coefficients? We know that the residual error, that is the error between our prediction and the true value for some row j, can be simply defined as the following. Y of j, that is the true value of y for that particular row j, minus our prediction of y hat for that row j. Next, since we're going to be minimizing the squared error, what I can do is just take the square of this residual error. Then, if I wanted to have a full summation of all the errors for m rows, that would simply be this calculation of taking the true value minus the prediction, get that residual error, square it, and then I could sum this up for all rows, that is m rows. And if I wanted the average squared error value, I would then simply say divide this by m, that is multiply it by 1 over m. And here I now have a calculation for the average squared error of my predictions. So keep this specific formula in mind because it's very close to what we're actually going to try to minimize. And it's pretty much exactly what we need for a cost function. So now that we understand a way I could write out my average squared error, let's develop it from the cost function side. So I'm going to define some cost function j, and we choose j just by convention notation, and you'll realize that if you're familiar with linear algebra, this kind of feels and looks a lot like a Jacobian, so that's where the j is coming from. And here we can see that we have this function of beta coefficients. And so what we're going to do is we're going to say that this function j of some beta coefficients is a cost function defined by some measure of error. This means we wish to minimize the cost function. I want to choose the values of beta that are going to minimize my error. And we actually just showed you the calculation for that error. So that means our cost function can be defined by the squared error. I'm going to say my cost function j that takes in some beta coefficients is going to be equal to this actual average error. Now, a couple things to note here is the lowercase j stands again for the specific data row. And then I'm taking the average by summing them up, all those squared errors, and then dividing it by 1 over m. So I want to minimize the cost for a set of betas. And the error between real y and predicted y is just y minus y hat for some row j. And then I'm going to square it. What's also nice about squaring is it corrects for negative and positive errors. And then I'm going to sum it for all m rows, and then divide it by m to get that mean. Now you're probably wondering, where did this 2 come from inside the denominator? It wasn't there before when we calculated the average squared error. Well, recall that when you're trying to minimize something, typically what you end up doing is taking the derivative and setting it equal to 0. So we will be taking a derivative here, and minimizing some function is the same as minimizing half that value. So we can easily just manipulate this by saying 1 over 2m instead of just 1 over m. And the reason for that is it's really just going to be for convenience. When we take this derivative, that 2 is going to come down and cancel out with that denominator 2. That way, it's technically the same thing since we're actually performing a minimization. So mathematically speaking, searching for a minimization is the same as searching for half that minimization value. And this 2 in the denominator is simply for convenience on a derivative. It just makes the math a little cleaner. And again, what is y hat? Y hat is a function of betas and features. That was the very first formula we showed in this presentation. So I can substitute in what I know y hat, or our prediction, is going to be equal to. Our prediction is going to be equal to that beta coefficient multiplied by that feature value. And then recall from calculus, to minimize a function, what you do is you take its derivative and set it equal to 0. So here what we're doing is we had our cost function j of some beta values, and we're taking the derivative with respect to those beta values. And notice now that when you take the derivative, these 2's end up canceling out to give us the value below. And you may be wondering, how the heck are we supposed to solve that derivative? It's quite complicated. So it's actually not really feasible to try to find the solution for that derivative and set it equal to 0. Instead, what we end up using is known as gradient descent, which is a computational way to actually figure out the minimization of that cost function. So while I can represent this as some mathematical derivative, it's actually going to make more sense to try to what is essentially plotting this out and having a computational search for the minimization. This will be clearer when we actually visualize what gradient descent is doing. We'll first visualize it in one-dimensional space, and then we'll visualize it in two-dimensional space. And hopefully from there, you can see how computationally this is working for any n number of dimensions, that is, n number of features. So we'll discuss how gradient descent actually minimizes this cost function in the next lecture. I'll see you there.